Today's topic is kernel density estimation. This is a bit of an unusual place to start with our study of statistics, but I feel it does a really nice job of underscoring some of the perspectives that we want to have moving forward when we study other statistical models. So the scenario we want to have in mind here is a sort of generic one. We have some data points that are observed. In this case, we have hours studied along the x-axis and we have score on a quiz along the y-axis. And generally speaking, what you see is that the more hours people study, the better they do, with some drop off towards the end. So the general trend is something like that. And what we want to do is understand the probability distribution that these observations came from. So in the real world, we'll get actual data points, and we will not know the underlying density F. What we want to do is construct an estimator, which we'll call F hat, based on the observations, that does a good job of approximating this unknown true density F. And there are many things you can imagine doing, but maybe one of the simplest things you could do is just infer from each observation that there's probably some probability mass nearby that observation. So the fact that the observation showed up there is a reflection not necessarily of there being a lot of probability mass exactly at that point, but at or nearby that point. And we can represent this mathematically by choosing some shape and making a little pile of probability mass following that shape right around each point. So if we do that for all of the points, then we'll get the probability masses sort of piling up here in the middle and giving larger values in the middle, and slowly fading away as we move away from there. And that hopefully will generally reflect the shape of the actual probability density. So mathematically, the way this looks is that we start with some function called k lambda, and lambda is dictating how wide the pile is here. So each pile is going to be 2 lambda wide and 2 lambda tall. And what we do is we just make a pile centered at each observation. So if the variable along the x-axis is called x and the variable along the y-axis is called y, and if the observations are xi comma yi, as I ranges from 1 to n, where n is how many observations we have, then k of x minus xi, y minus yi is one little pile. And it's going to have total mass 1. So this function k lambda is going to be designed so that it integrates out to 1. So each pile should be 1 over n times k lambda of x minus xi times y minus yi. And then we'll sum that from 1 to n. And that function is going to describe the sum of all of these little piles of probability mass. So this is going to be our f hat. And since f hat depends on lambda, we'll put a subscript here to indicate that. So if we assume that our function k lambda is defined to be a product of two functions, one depending only on x and the other depending only on y, and if the function that we're plugging x and y into, called d lambda here, has support equal to minus lambda to lambda, in other words, it's 0 outside this interval and it's non-zero inside, then the function k lambda is going to have support everywhere that both x and y are between minus lambda and lambda. So if little x is between minus lambda and lambda, this part will be non-zero. If little y is between minus lambda and lambda, this part will be non-zero, and so the product will be non-zero. Conversely, if x or y is outside that interval, one of the two factors will be 0 and the product will be 0. So the exact shape of this kernel mostly doesn't matter too much. One option is to choose this function called the tricube function, where the cube refers to this 3 and tri refers to this 3. And this blackboard bold 1 or bold-faced 1 with a subscript means the function that's 1 when the condition in the subscript is true and is 0 otherwise. So this is just a way of saying outside of the interval from minus 1 to 1, make everything 0. Inside, make it behave according to this function, 70 over 81 times 1 minus absolute value of u cubed, all cubed. And the reason for this 70 over 81 is so that the whole thing integrates up to 1. Other possible kernel shapes include the density of the Gaussian distribution or the triangular function, which is 0 up until -1, and then it rises at slope 1 until it hits 0, and then comes back down at 1 and stays 0 after that. So in the second problem, we're going to use the Gaussian function as our kernel, and we want to see what the resulting kernel density estimator looks like. So D is defined as specified according to this formula. And then d lambda is going to be the same idea, but we're going to scale it. So we divide by lambda here. So you see that if u hits lambda, then this argument is 1, and we're at the right edge of the set of points where d is non-zero. Likewise, if u is minus lambda, then this quotient is -1, and we're at the left edge. So this function is going to be non-zero over the interval from minus lambda to lambda. So if lambda is really small, it's going to be very concentrated, and if it's big, it's going to be spread out. And we have to divide by lambda so that we still get a total integral of 1. So we can just make a u substitution and see this is the right scaling to get this whole thing to integrate up to 1. And it makes sense because if lambda is really small, then the support is really small, and the graph has to be tall in order to total up to 1 underneath. So k lambda is going to be d lambda x times d lambda y. That's just like we discussed above. And the kernel density estimator evaluated at a particular point x comma y is going to have this structure that we discussed. So we sum k lambda x minus xi, y minus yi, where these pairs range over the observations in our sample, and then we divide by how many of them we have. So we're going to make a scatter plot here with the points from our observations, and then we're going to make a heat map to illustrate the values of the kernel density estimator. So the function that we want to plot is the function which maps each ordered pair x comma y to the kernel density estimator associated with lambda and the particular sample, a set of observations. And then we have some setup for this particular situation that's featured in the data gymnasia course. So we have a function 2 plus 1/50th times x times 30 minus x. That represents the score that you're going to get if you study x hours on average. There's a lot of fluctuation around that value, and that's going to be represented by this standard deviation in the vertical direction. So we integrate the density function for x and use the inverse CDF trick to generate x from its distribution. And then once we know x, we generate y from its conditional distribution given x. And we generate a bunch of observed samples, and we're all going to get the same ones because we set the random number generator seed here at the beginning. And we'll get to plot what the kernel density estimator looks like. So it looks like 1 is a pretty good value here. The heat map is showing you that there's more mass in the middle, and it sort of tapers out as you move away. And that seems pretty consistent with the original density function that we looked at over here. It's important to see what happens if we choose lambda too small. The density is going to be very concentrated around each point. So what you can see is that there's just a very, very small amount of mass piled up right around each point. And this looks like it's clearly taking the individual points too seriously. There's almost no probability mass in this open space. And really there should be. The fact that there are points above and below is an indication that there just happens to be a lacuna here in the actual set of observations that we see, but it's not a reflection of the underlying probability measure. At least that would be a reasonable assumption. Likewise, if lambda is too big, then the probability masses are spread out too much, and there's a lot of probability mass far away from where all the samples were observed. And also we end up with a very wrong shape here, and that's because we're putting probability mass in squares. So it's going to be, when lambda is large, we're going to see that sort of square bias in the form of this density function kind of being more circular rather than elliptical. So we want to use a lambda value somewhere in between, like maybe 2, and that looks pretty good. So the next part is the trickiest part. We'll walk through it. The idea is that we want to come up with a better way to choose lambda. There is still this parameter in this density estimator, and it would be nice if we had some meaningful way to choose lambda. So that's going to require us to do a little bit of probability review. So recall from probability that if you want to calculate the expected value of some function of a random variable x, assuming that x has a density, you can do this by integrating that function g multiplied by the probability density function of that random variable. Likewise, if you have a random variable that depends on two random variables, let's call them x and z, and you want to find the conditional expectation of that random variable g of x comma z conditioned on z, then we'll do the same thing. We're going to integrate the value that we want to take the expectation of, and then we're going to multiply it by the density for the randomness that we're integrating out. So we're conditioning on z here. So z is going to stay random. It's treated as a constant. And x is the quantity that's being integrated out by this expectation. So the probability mass we should multiply here is the probability mass associated with x conditioned on z. So we see z, whatever z is, we need to ask, okay, what does x do based on z? And that's going to give us some probability density. And then we multiply that against the value that we're taking the expectation of. And if we can say that x and z are independent, then the conditional density of x given z is just going to be the density of x. So bear this formula in mind as we move forward discussing the kernel density estimator. So we start with the idea that what we want to minimize is the integrated squared difference between f lambda and f. So if f and f lambda look like this, that would be a good situation because f hat lambda is close to f. And one way to quantify that is to measure the squared difference between the graphs from minus infinity to infinity and just total it up. This is called the integrated squared error. And directly estimating the integrated squared error is out of the question because we have this function f, which in a real-world situation we will not know. That's the true underlying density, and we only know that by way of the observations. So this seems hopeless, but let's plot ahead anyway. We can square the binomial and distribute. And some good things happen. This term we can ignore because what we're trying to do is minimize the integrated squared error. We're trying to make this whole thing as small as possible. And this first term has nothing to do with f hat. We don't get to control the first term. So we get to ignore that one completely and just try to make the other two as small as possible. This last term is also fine because it deals with f hat lambda. That's a quantity that we've defined in terms of the observations, and we're going to be able to estimate this numerically. This middle one is the trickiest one. It involves f hat lambda, so we have to care about it, and it also involves f, which we don't know. However, if we look back at this formula, we can see that if you want to integrate a function times the density function, then that's the same thing as the expectation of that function. And this is approximately the same thing as sampling n times from the distribution of this random variable and averaging. So as a first pass, we might think, is it the case that this integral can be approximated as just an average of the value we get when we plug in each observation into the estimator? And the answer is no, because when we did this calculation back here, this step assumes that x and z are independent. So z here is going to be the stuff that we're conditioning on, and x is going to be the sample that we're plugging in. And the stuff that we're conditioning on, what the function g depends on, includes all of the x's. So if we look back at this expression, this f hat lambda quantity depends on all the xi's. Because remember, we defined it by putting a small probability mass around each of the xi's. So this function is getting to see all of the xi's. In particular, it's going to see this xi that we're plugging into it here. And so that's going to be a problem. So this does not work. However, what we can do to salvage the situation is instead form an estimator which leaves out the ith observation. So we're going to call that f hat minus I in parentheses like that. And that just means ignore the ith point, look at all the other points, and put small probability masses around each one according to the same rules. And then we're going to plug in that reserved ith observation into that function. And now this approximation is fine because f hat minus I depends only on all the x's other than xi. And now this random variable z really is independent of xi. So in the end, we arrive at this quantity that we want to minimize. The integral of f hat squared, that was that third term that we said we could approximate just fine. And then minus 2 times 1 over n times the leave one out estimator evaluated at the ith observation. So that might seem a bit abstract. So what we're going to do is plot a density function, plot the corresponding kernel density estimator, and show that these values, integral f hat times f, and then this average, really are close to one another. So first we're going to do the full kernel density estimator, which takes tricube of lambda, centers it at xi, where xi ranges over the full list of observations, which we called x here. And then the leave one out estimator is going to be very similar, except we have to make sure to leave out the ith observation. So what we're going to do, instead of calling this little xi, we'll actually index capital X. And so we have to iterate over the indices of x rather than x itself. And then we can say, oops, I should have called this j since I have I in my argument list. And then I can just exclude the term where I is equal to j. And now we can plot, and what we see is that for this particular value of lambda, it's pretty terrible. So for one thing, we only have 10 observations. And this lambda is really, visually here, it looks like it's too small. There's a lot of humps, and we're very far off from this true density. So if we increase lambda, it might do a bit better job. So that's somewhat better. The cheating way to do better is just take many more samples, and you're going to see that it gets rather close. It's still not quite closing the gap here because the shape of the tricube function is influencing the shape of this estimator since lambda is quite large. If we decrease lambda, then we're making smaller piles, and each probability mass is being taken more seriously. So we're going to be able to get closer. So what we wanted to look at was the integral of f times f as compared to this sum obtained by averaging the leave one out estimators evaluated at each left out point. And we're going to approximate integrals in the simplest way possible, just with Riemann sums. So we're just going to make a small delta, and then we're going to evaluate the function that we're trying to integrate for x ranging from, let's say, minus 10 to 10, because you can see both of these densities are getting really small, even by 3. So if we go from minus 10 to 10 in steps of delta, then we're not leaving too much out on the extremes. We need to multiply by delta, so that's like your dx and your integral. So you calculate the value of the function at each point, sum them up, and multiply by delta. So the first function that we're trying to integrate is f hat times f. So again, in this situation, we actually do know f because we're making this stuff up just to see how it works. In a real situation, you would only get the sample, so you would only know f hat. Okay, so we're going to sum this up, and we can take these brackets away, and we get a value that's about 0.279. And then the other function that we're trying to approximate is the average of the leave one out estimator. So the for argument f hat was our leave one out estimator. I indicates which one we're leaving out, and then xi is saying where we're evaluating it. And we're going to do this for each index of the vector x. We see that our value is very close here. And if you're thinking, well, did we really need to leave one out? Let's try it that way. So same idea, except I'm going to use the 3-argument version of f hat, which does not leave one out. And in this case, it actually does turn out to be quite close. And this is going to happen typically when lambda is around a good value. However, to show you that it can be quite far off, let's take a small value of lambda. So that our estimator is very spiky here. And try again. So these are still close, the leave one out average and the actual integral we're trying to approximate. And okay, that wasn't small enough, so it's still reasonably close. So it's now really way too small. But again, these are still pretty close to each other. And now this one is way larger, 0.36. And what's happening here is that f hat lambda, the full estimator that's getting to see all of the samples, it's putting a really tall pile of mass right around the actual sample xi. So when we ask, hey, what's your density at this particular xi? It's like, well, it was pretty big because I saw that before and I already put a big mass there. So as lambda gets really small, this is going to get bigger and bigger. So neglecting to do the leave one out is going to lead to arbitrarily large j values, and we're not going to get a sensible estimator. So now let's think about how we would approximate the regression function. In other words, the function which tells us the conditional expectation of y given x. So this is often what you're interested in if you want to make a decision. For example, in the context of our hours studied and the score we're going to get, we'd be interested in knowing not our exact score because that's not going to be predictable, but the expected score given the number of hours that we studied. So that's the expected value of y given that particular x value. And our idea based on kernel density estimation is that once we have an estimate of the density, we can just take a conditional expectation for that estimate and come up with an estimate of the regression function. So to simplify the situation, we're looking here at a much smaller number of observations, so you can really see each pile of probability mass. For this set of observations, you would actually want a larger lambda value, but we're using a smaller one here because it's easier to reason about. You don't have the squares sort of like blurring into each other. And what we're going to observe is that for a particular value of x, like this one, there's going to be some probability mass along the line. For example, there's mass in here, and there's mass here, and everywhere else it's 0. And what we're doing is taking an average of that mass. We're just finding the middle. In this case, eyeballing it, it looks like something like right here, finding the balance point of the probability mass along that vertical line. And what you can see is that by symmetry of the function d, which is dictating what the shape of the mass looks like for each of these points. For example, here it's kind of coming up and then back down like that according to the shape of d. So d is symmetric, so all of that mass is going to average out as though it were just right at this point. So we can do that for each of them. The part that's above and below is going to average out to be exactly at this point, and similarly for this one. So basically it's just going to be an average of the points that contribute, except that points will contribute less if the observation is farther away. So if this vertical line just barely clips the edge of this square and it goes more through the heart of these two squares, then those two squares in the bottom are going to contribute more. So in other words, our estimator, r hat, is going to be an average of the yi values. So it's averaging the y values at the observations. And the weights are going to be based on how far away the x-coordinate of that observation is from this particular value of x. And the function which dictates how the contribution decays is the function d, because that dictates the shape of the pile horizontally. So we want to do a weighted average, so we need to divide by the total of the weights. It doesn't hurt to just sum over all n observations, even though we're ultimately interested in only the ones that intersect that vertical line, because d lambda of x minus xi is going to be 0 for all these points that are too far away to contribute. So just for simplicity, we'll include them all. And so we get this formula for the estimator. And there's a lot of notation here, but don't worry about that too much. It's just telling you a weighted average of the yi's. So we can plot that to see what's going on. So if we're using the tricube kernel, we'll compute tricube of x minus xi, and then we multiply that by yi, and then we'll sum those. And then we need to divide by the sum of the weights. So same thing, but without the yi. And we get something that looks like this. So it does a reasonably good job of approximating the actual regression function, which, remember, in this case we know because we made this stuff up. And you can adjust the value of lambda and get different results. So for example, if lambda is way too large, then it's sort of too flat. It's not able to respond locally to the information about that particular x value. And if lambda is too small, then it gets way too staticky. It's going up and down a lot. It's too local. It's paying too much attention to what's happening right around that point. And it's not getting enough information. So somewhere in between, it's going to be better. And another point to make here that's kind of interesting is that the estimator is going to curl up at the end. That's not just a random fluctuation here. That's systematic. And what's going on is that the observations which contribute to the regression value here, some of them are way on the left edge, but other ones are to the right a bit, and the mass sort of leaks out to the left because we're putting a sand pile around each point of probability mass. So some of that mass is going to be over here to the left. So this red value here represents an average of what's going on all the way at the left edge and an average of what's going on a bit to the right. And that averages out to be a little bit high. And you don't see it curling down like that over here in the middle, because a little bit to the left and right, one of them is up and the other one is down. So those contributions are going to kind of average out, and you'll end up usually in about the right spot. But you see there's some curling on this edge too, and it's a little bit less because the graph isn't as steep over here. But that's a feature of this estimator around the endpoints of an interval. So let's compute the approximate squared error between r and r hat. So we'll just follow our nose here. We do r hat minus r. We square that. We cover our whole range from 0 to 20. And then we'll sum that up. And also multiply by delta because we're approximating an integral. We get 1.86. And if we want, we can plot the error for lots of values of lambda. So this is our error. We can plot from, let's look between 1 and 2. The function that maps lambda to this error associated with lambda. And let's call it ISE for integrated squared error. And we see that when lambda is too small, our error is too big. When it's too big, our error is big. And there's a point somewhere in between where it's just right. This is the best we can get. And we can find that value if we want using the package optim. And there's one little hack we have to do here, which is that optim expects its arguments to all be vectors. So we have to treat lambda here like a vector containing a single number rather than just a number. So we'll map the vector lambda to this function, and this first function is just pulling out the entry, the first entry, which is the only entry from this one element vector. And then we need to say where to start, which again has to be a vector. And let's just start at 1. So the optimization will start here, and then it'll go down into this well and find the smallest value. And we have to choose a method. If we try to run this without specifying a method, it tries to use the Nelder-Mead method, which doesn't work for univariate functions. So standard choice is BFGS. And what we find is that the minimizer is about 1.39, which is here, and the minimum value is 1.62, which is there. So to recap, the main ideas are that we can approximate a density by putting a small 1 over n probability mass in a pile around each observation. And the parameter lambda, which governs how wide each pile is called the bandwidth. We can estimate a good value of lambda from the data by minimizing the integral of f hat squared minus 2 over n times the sum of the values we get by forming a kernel density estimator with bandwidth lambda, leaving out the ith observation, and then plugging the ith observation into that estimator. Lastly, the regression function associated with a kernel density estimator, called the Nadaraya-Watson estimator, is obtained by taking an average of all the yi's with weights given by the kernel function evaluated at the corresponding x position.